The most common thing a text editor does is insert or delete a few characters somewhere. If the whole document lives in one contiguous character array, inserting at the front shifts every remaining character. The rope is the data structure designed to fix exactly this. So first, let's pin down what makes a flat string slow, then we'll see how a rope changes the game. Start with an ordinary string, all characters laid out in one contiguous block of memory. Reading by index is fast, but inserting or deleting must move everything after it, which is big O of n. Concatenating two long texts copies both blocks as well. The bottleneck is now clear, huge contiguous copying. A rope takes the opposite approach and stores the text as many small chunks instead of one big block. A rope is a binary tree. The actual text lives only in the leaves, each holding one short chunk. Neighboring leaves hang under internal nodes. Reading the leaves left to right gives the whole document. Internal nodes store no text at all, just a weight, how many characters its left subtree holds. N1's left side is hello, so its weight is 6. The root's left side is hello world, so its weight is 12. Now that the structure is in place, let's see how those weights help us jump straight to a character. With the text split apart, how do we find character 15? The weight values answer that. Start at the root. Index 15 is not below the weight 12, so the target is not in the left subtree. Go right and subtract 12, leaving 3. That N2, the new index 3, is below its weight 8, so the character sits in the left subtree. Go left and keep the index. We land on the leaf this is and take its character at index 3, the letter S. The whole lookup walked a single root-to-leaf path, which is big O of log n when the tree is balanced. Once position lookup is this efficient, the next question is whether edits can stay just as local. Now, concatenate this document with another piece of text, today. No characters are copied, just allocate one new root and hang both trees under it as left and right children. The new root's weight is simply the left subtree's total, 26. This is one of the rope's nicest properties. Concatenation is almost just tree wiring. Next, let's flip that around and see how to cut one rope into two. The mirror image of concatenation is split. Cut one rope at a given index into two ropes. Again, we descend using the weights. Index 12 equals the root weight exactly, so the cut lies right between the two subtrees. So we detach the root's two edges. The left rope is hello world, and the right rope is this is a rope. If the cut falls inside a leaf, that leaf is split into two shorter chunks, and the nodes along the path are reassembled. With split and concat in hand, insertion falls out for free. First split at index 12 to get a left and a right rope. Turn the inserted text big into a leaf of its own. Then, concatenate twice. Join the new leaf with the right half, and put the left half in front of that. The result reads, hello world big. This is a rope. No existing leaf was copied. Only a handful of nodes along the path are new. So what about the reverse move? Can deletion be just as clean? Deletion mirrors insertion. Suppose we just inserted big and now want to remove it. First split at index 12. The left side keeps hello world, and the right side starts with big. Then split the right half again by length 4, isolating the middle chunk, big. Discard that middle chunk, concatenate the two outer ropes, and the document becomes hello world, this is a rope again. So, deletion is really two splits plus one concatenation, again touching only nodes near one path when the tree is balanced. At this point, the core rope editing pattern is complete. Now we can pull the whole idea back together. A rope keeps text in small leaf chunks and records the left subtree size in each weight. When the tree stays balanced, indexing, splitting, inserting, and deleting are all big O of log n, and concatenation is big O of 1. The trade-off is slower random access than an array, and repeated concatenation can still make the tree degenerate. So real implementations often pair big O of 1 concatenation with later rebalancing. Ropes also share structure naturally, which makes them a good fit for editor undo and collaborative editing.